Welcome back. So as you recall last time, sorry, this is segment 2, section 2.1. As you recall last time, we had finished proving the Pythagorean theorem, and granted, I mean, the proof of it was based on some things that aren't, well, we haven't rigorously proved them either, but it hopefully did show you a little bit of insight into why this equation has to hold for right triangles in plane space. So now that we have the Pythagorean theorem, we would like to use some of the results of the previous chapter about sort of the definition of the trigonometric functions to produce a couple of new mnemonics that will help us as we try to attach the sort of definitions of these functions to regular geometric shapes. In this particular case, and for the next couple of sections, we will be talking about right triangles. So in every situation, we are talking about a triangle that has a right angle somewhere, and then two acute angles. So we're working basically on trying to find the trig functions of a couple of acute angles. Is sort of the big picture idea. So let me start by sort of giving, and I'm going to start on the same page we had before. So we're still on page 2, but I'm going to start by just kind of drawing a sort of standard triangle. And I mean, we've done it before, but I want to make real clear that when, and it's sort of a cadence, it's sort of a normal way of doing these things, that when you have a triangle, whether it's right or not, doesn't really matter, but we're talking about right triangles for the time being. If you have labels that represent either the vertices, points, if you will, that represent the vertices, and as long as it's understood, those point labels are also used for the measures of those angles. So in this particular case, I might call this triangle ABC with capital letters at the vertices, because the vertices are represented by points. But these A, B, and C can actually represent the measure of the angle as well, as long as it's understood. It is common and almost universal to use a capital letter, and then for the opposite side, to use a lowercase letter that's identical to represent the length. So in this case, this would be length A, B, and C. Very standard stuff. So I wanted you to see it, and just remember that this is kind of in the absence of any explanation as to what those, and like I said, it doesn't have to be a right triangle, it can be any triangle. Unless it's actually stated, the measures are always going to be the interior angles. But if you had like a complex structure that had a number of triangles all sandwiched together, you might have a situation where you have to specify with 3 letters what angle you're talking about. But we're not doing a lot of heavy geometry. So one thing that I want to talk about is let's consider for a second how we would represent the if we imagine this superimposed on a coordinate system, and maybe the way to look at this is maybe in reverse. That might be a little bit easier to see, but it's not really critical. I want you to consider for a second if we were thinking about the trigonometric functions of side B, of angle B, okay? And angle B, if we're measuring it, and it should have a positive angle, right? All interior angles are positive. Then if we were to superimpose, let me just kind of draw this to the side. This is angle B, right? It has a ray that extends forever, but when we attach it to this specific triangle, it's the positive measure. So this, what we're calling over here side AB, well, actually, to be careful, is ray BA. It's repeated there. And what we will end up doing with this is we will, as I said, we've superimposed it, but recall that if we were kind of looking at this sideways with the initial ray superimposed on the x-axis, that the sign of this function is determined by, or the sign of this angle is determined by the y coordinate divided by an r value that's associated with it. Okay. Now this happens to be this particular triangle, and we know exactly what those values are. It would actually be b over a. So in this particular case, sine of angle b is equal to b over a. And similarly, we could do that for cosine and tangent, and we'll kind of we'll leave it at that. So cosine of angle B is equal to, now again, in this particular case, it's not the y value, and I know I've kind of intentionally sort of screwed this up so that the coordinate system isn't clear, but instead of being b over a, it's actually c over a. And then finally, tangent of b is equal to sort of the y value, b, over the x value, c. So b over c. Now, you may recall that there were some names that were associated with these different sides based on being a right triangle. And so I want to start invoking some mnemonics. If you have an angle, acute angle B, then the side that is opposite it, obviously, is called the opposite side. The side that is next to it, that's still a leg, is called the adjacent side. And the hypotenuse is, of course, the hypotenuse. So in an arbitrary triangle, right triangle, for any particular angle, the sine of that angle can be remembered as being the opposite, and I'm abbreviated, opposite over the hypotenuse. And the cosine of that angle would be the adjacent over the hypotenuse. And the tangent of that angle is the opposite over adjacent. Now, as long as you know what opposite, hypotenuse, and adjacent mean, this sort of devolves into a mnemonic, which is so, ka, toa. And I have seen many students use this and write this on their tests and everything else. So a sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Now, do not confuse the mnemonic for some kind of universal result. Remember what all the hypotheses are. The angle has to be an acute angle. The triangle has to be a right triangle for all these words to make sense. And the opposite side depends on which angle you're talking about. Because remember, in a right triangle, there are actually two acute angles. So if you shift to a different angle, then the opposite and the adjacent side flip around. So this is sort of the classic right triangle trig mnemonic that is developed in almost every trig class at some point. So what do we do with that? One thing to observe is that before we get into actually using it to solve triangles, what I'd like to do is I'd like to make some additional observations. So let's go back to this triangle that we had. And we don't need the full thing, so let me just, well, what did I had A down here. Okay, so B and C, and C, B, A. Okay, so note that there's a relationship between B and C. Note that B is equal to 90 degrees minus C. Now, do you remember what that means? The relationship between B and C in this particular case is that they are complements of each other, right? They are complements. B and C are complementary angles. Right? They add up to 90 degrees. Well, if you're wondering where the names of these different functions come from, this is where it comes from. It's the co in complementary, and I'll show you exactly what I mean by that. So if we were to say, look at the sine of angle B, notice that that is B over A, right? So it's the opposite over the adjacent, but that also happens to be the cosine of C, right? Think about it. C here is the adjacent over the hypotenuse. So again, B over A. And if we make this little sort of substitution up here, actually I want to do the reverse. This will be cosine of 90 degrees minus B. So, all right, what is this? What is the thing to learn from this? This is not specific to right triangles. We used a right triangle to show it, but this is true no matter what. The functions themselves have this property that the sine of any angle is equal to the cosine of the complementary angle. Okay, so sine, angle, cosine, complementary angle. And that's actually where that co comes from, because there's an equality there. These, with this sort of idea, we can develop, and it turns out that you can reverse the order too, right? Cosine of the angle is the sine of the complementary angle, or whatever. But we develop from this a number of additional, what are called co-function identities. And here they are. So, and we'll get away from A, B, and C here, but sine of theta is equal to the cosine of the complementary angle. And similarly, cosine is equal to the sine of the complementary angle. It turns out that this is replicated for all of those pairs of functions that have sort of the same name and a co in front of them. And like I said, this is actually where those terms come from. So tangent of theta is equal to the cotangent of the complementary angle. And cotangent of theta is equal to the tangent of the complementary angle. Secant of theta is equal to the cosecant of the complementary angle, and cosecant of theta is equal to the secant of the complementary angle. So these are collectively, these six equations are the co-functions. Now I will just tell you that we don't use these functions very frequently. We don't use these identities very frequently. There are a couple places where we need them. And when we actually do use them, they become sort of critical. But it turns out that these particular functions are a special case of what are called the sum and difference identities that we'll see in chapter 5 in section 3 and 4. So we'll use them sparingly, but when we do use them, they make our work much easier. But I want you to just point out, I just want to point out, this gives us a new way to relate some of these functions, right? Here we have a direct, we don't have any, we have, and I kind of want to draw attention to these two, cotangent and tangent, because those are already related by a reciprocal identity. And now we have them related by a co-function identity, and there's some interesting things that come out of it as a result. I mean, we're not ready for that quite yet, but I just wanted to point out that there is some more to come. So, and as I said, these results are independent of actually triangles. We don't have to, I mean, we use a triangle to kind of show it, but it certainly works in other cases. So I think my video is getting just a tad bit long here. I want to come back in segment 3 and do some work it out kind of examples where we look at a specific triangle and calculate the exact value of at least, well, the 6 basic functions. So I will stop this recording here.